Hello, everybody. I'm going to try and be a bit mobile, which is going to be challenging because I've got 3 things to hold and only 2 hands, but we'll see how it goes. I am going to mention AI. Lock the doors. So yeah, I was thinking about, and by the way, it's lovely to see so many familiar faces. I joined JUXT just over a year ago, and the Christmas party was the first in-person event that I joined. And it feels particularly special to me to be here and to see some new faces as well. And I'm looking forward to getting into the festive spirit later on. And I was looking at this venue. It's a great venue, and the exhibition that's on upstairs, I'm looking forward to seeing that. And I saw this, let's see if I can do this, yes! This marketing picture of an installation which is aiming to convey the awe of a quantum multiverse. And I was looking at this and thought it's actually a great visual metaphor for what it's like to be sat at my desk interacting with an LLM. Like there, you know, just the other side of a computer screen is this awesome 500 billion dimensional fractal, utterly incomprehensible. Now, this is by a guy called Conrad Shawcross, and he graduated from the Ruskin School in 1999. And coincidentally, the first coincidence of this talk, there's another person in this room who graduated from the Ruskin School 6 years later, and that was me. Because I took a circuitous route to programming via a studio-based fine art degree. And so actually the way that I learned programming was doing things like putting a filing cabinet in the atrium of a hotel in London. It was there for a month. The top drawer was propped open, fixed open. In fact, when you looked inside, you'd see a person or people peeking out. And all of those people were recorded by the filing cabinet, because actually there was a camera inside. It was pointing through the screen because the screen actually was a half-silvered mirror. And everyone who looked at the piece was added to this ever-growing, looping playlist of everyone who ever looked at the piece. So, you know, and you could see, by the way, when you looked at the recordings, the moment that people realized that they too were being recorded. I don't know if you could get away with that kind of thing now, but this was 20 years ago. And I was really into the idea of quantum theory and that you could affect things just by looking at them, James's Heisenberg, but also the idea of kind of replicators, these sort of actions and reactions that would be permuting and combined over time. I also did this in a modern art gallery in Oxford. It's a resin bulb. It's got a blue LED inside it. Sometimes it's on, sometimes it's off, sometimes it's kind of blinking erratically. And the whole assembly is attached to a ceiling switch. And there was a little sign letting people know that they could touch it. And if you tugged it, you'd get this satisfying clunk, and nothing would happen, right? Or at least nothing would appear to happen. But sometimes you'd see a kind of blink in the light later on. And then maybe you'd be going around the gallery and you'd see another one elsewhere. And maybe you'd realize that these two were actually entangled. And what you were doing when you pulled on one was controlling the light in the other and vice versa. And so actually there was no automatic switching going on. The light was purely, it was people kind of talking to each other. And I called these Turing bulbs, and I was really interested in the idea of a kind of reverse Turing test, where all you've got to play with is a 0 and a 1. And how would you convince somebody, if they didn't follow the wires, that there was another person at the other end? So I read a book by Deutsch. Eternal Golden Braid, Gödel Escher Bach, was my Bible around this time, and I sort of carried it around with me wherever I went. But a few years later, I read a book by Deutsch, and the second coincidence of this talk is that last year at the Christmas party, Malcolm held up, I think it was this book, The Beginning of Infinity, by David Deutsch. But really, it was The Fabric of Reality that was the book that really affected me, and I read it a few years after graduating. And it's one of those big books, because in it, he asserts that our deepest understanding of reality emerges from the interweaving of four fundamental theories. They are the theory of evolution, which is specifically the gene-centered view, the idea of replicators, and that organisms and species are just the vehicles that genes use to replicate. And this, of course, isn't just a biological theory. So you read The Selfish Gene. Dawkins talks about memes. This was before internet memes really became a thing, but ideas that could replicate and adapt through human brains. Quantum physics, specifically the many worlds quantum theory, which takes as physical fact the kind of mathematical idea that there is an ever-branching multiverse. I'm looking forward to having our minds blown about that later on. Universal computation. I don't think I need to go into that too much with this audience here, but the idea that a computer is a universal simulator, can simulate any physical process, of course, including another computer. And epistemology, the theory of knowledge. How it is that we can come to know anything at all, particularly things that we can't interact with directly. And the thesis of the beginning of infinity is this idea that 500 years ago, the Enlightenment, which kicked off the scientific revolution, was not just a significant kind of human cultural event. It was a momentous moment in the universe, as far as we can tell, because it started this process, which is still going on, of enormous discovery and understanding, which, all being well, will continue indefinitely. And as he says early on in the book, there will always be problems, but also all problems are soluble. So we've got our very own John to thank for this image of SH86. He posted it in the Astronomy Guild channel about a week or two ago. So the history of astronomy provides this amazing kind of lesson in how it is that we can come to know things. You have Ptolemy, who had the geocentric view of the solar system, where you had perfect spherical celestial bodies orbiting in perfect circles because the heavens were perfect. But in order to match up to observation, you needed to invent these elaborate extra circular orbits called epicycles. It's sort of orbits within orbits. And it worked. You could actually make cardboard models, and people did. The sailors used them for navigation. Clergy apparently used them to predict when Easter was going to happen. So it was a workable model. But all of these epicycles were it's like an extra parameter in a machine learning model. If your theory can't explain something, you just add an extra parameter, extra degree of freedom. And if your theory can expand to explain anything, then it explains nothing. So Copernicus came along and proposed this idea of a heliocentric universe. So we do away with the epicycles. So this is a better theory, but we've still got these perfectly circular orbits. And then Kepler painstakingly analyzes data for years and years that was itself painstakingly collected by Tycho Brahe, and comes up with the idea of elliptical orbits. Not everyone gets on board with that idea, including Galileo, who for his entire life maintained the idea that orbits needed to be circular. But the major contribution of Galileo is that he was able to see the phases of Venus. And in the geocentric model of the solar system, Venus was always between the sun and Earth, so it would kind of always be a bit backlit. But he was able to show Venus in full illumination, which was the nail in the coffin for the geocentric view of the solar system. And And he did that through this new invention of the telescope. And he hand ground his own lenses, and although he didn't invent the telescope, he took the technology from something like 3 times magnification to 30 times magnification. But his contemporaries were really uneasy. Said things like, how can we trust a device, a tool that shows us something that we can't easily verify by other means? And in fact, the early telescopes had aberrations and imperfections. That means you'd sometimes see 2 stars when actually there were 1. Sometimes you'd appear to see a star where actually there was nothing at all. But even Galileo's friend, Cesare Cremonini, said, I do not wish to approve of claims about which I do not have any knowledge and about things which I have not seen, and then to observe through those glasses gives me a headache. Enough. I don't want to hear anything more about this. Now, I don't know about you, but this sounds to me like many of the criticisms of AI. And this guy wasn't a fool. He was absolutely right. Because what it required for the decades that it took to make better telescopes was this kind of judgment about when you were seeing errors versus when you were seeing genuine insight. And at the moment in AI, I kind of think we're at the hand-ground lenses stage. And there are so many examples that I could pick, but here are a few. You've got the reversal curse. It's when you train models on things like, well, all about Tom Cruise. And you ask, instead of who's Tom Cruise's mother, who is Mary Lee Pfeiffer's son, the model isn't going to know. It hasn't learned a fact. It's not something that it can navigate in both directions if the training data has always just been about Tom Cruise. It's not generalizing very well. The models can get confused by irrelevant information. Here's a sort of maths question about how many kiwis Oliver has when he picks a few on Friday and some on Saturday and Sunday, but 5 of them were a bit smaller than average. Models these days are going to subtract those 5, even though size has got nothing to do with quantity, because everything's weighted, including the noise. And it's not just text. Vision models exhibit very similar kind of issues. If you take a cat and you do style transfer to give it a kind of elephant hide, models these days will still often get confused and think they're looking at an elephant. So my hunch is that a lot of the kind of negativity around AI, apart from the hype, which many of us have an aversion to, is that what we intuitively see are that these are kind of epicycles. These aren't just imperfections in a telescope lens. This is a fundamentally flawed technology. And I've got a lot of sympathy with that point of view, because when I first got into data science and more specifically deep learning, I had this idealized hope that we might be able to look into the hidden layers of a deep network and learn something meaningful about the world. And there were early signs that that might actually happen. Like 12 years ago now, Word2Vec was for its time a large network, and you could do this kind of vector arithmetic on words. You could take the word king and subtract man and add woman and get the word queen out. It felt like the model had really learned some meaningful relationships. But in spite of all of the research done by Anthropic over the last several years, it doesn't seem like this simple interpretation has carried over at all to deep networks and LLMs. The researcher Kenneth Stanley has trained 2, albeit quite small, neural networks that generate a graphical image of a skull. One of them is trained by stochastic gradient descent. And here he's visualizing the hidden layers, the latent representations within the model as a heat map. Stochastic gradient descent, as you probably know, is where models are kind of incrementally and iteratively improved by heading towards improving some kind of cost function, which will lead to some kind of optimal solution, we hope, but with no guarantee that it's going to be a global optimum. You might find yourself in a local basin. When you look at these representations within the network, they're total spaghetti. They're fractured and entangled. There's no symmetry that you see in the output image in any of the internal representations. And there's no guarantee that the LLMs like Claude and ChatGPT, in spite of their massively larger training regime, are different internally. So what we're looking at here is the result of the network. Each one of those is a matrix which will get multiplied together to produce the output. But Kenneth Stanley also looked at other ways of training neural networks, like an evolutionary algorithm. And here you can see very different internal representation. Exactly the same output, but those internal representations, the hidden layers, look almost like they were designed, but they weren't. But we don't have to reach for evolutionary algorithms. Also just invent better architectures. And researchers are doing that. There was a paper from 2020 called Intelligent Matrix Exponentiation. And it was from Google Research, and they identified promising new ways of doing high-dimensional and intricate classification with complicated decision boundaries. Using a spiral data set, on the left-hand side, you can see a kind of standard approach, the rectilinear activation function, which is kind of ubiquitous in deep learning and in LLMs, which has perfectly classified the data. I don't know if you can see, it's a kind of wibbly and wiggly decision boundary, which beyond the bounds of the data it has this sort of air of arbitrariness about it. You contrast with the approach that they were investigating, the M layer, like Kepler. The model had learned some regularity about the data, in spite of the fact that there was nothing within it that predisposed it towards spirals in particular. So AI at the moment is obsessed with benchmarks. It's quite hard for a new paper or a new model to gain traction if it's not advancing the state of the art. This model, in spite of being proposed in 2020, didn't advance the state of the art in terms of benchmarks, so it's not seeing a great deal of traction, in spite of it being quite a promising avenue of exploration. It's almost like the industry as a whole is performing this kind of gradient descent, where if you're not working on some kind of transformer architecture, you're not going to be able to optimize and make some kind of incremental improvement, which constrains the kind of research that we're seeing. And yet almost no prerequisites to any major invention were invented with that invention in mind. You know, the lenses of Galileo's telescope weren't invented for telescopes. They came from reading glasses. The vacuum tubes from early computers came from amplifying telephone signals. Each stepping stone was necessary for the discoveries that followed, but you never could have planned that in advance. You can't optimize towards something that you can't conceive of. So the thought I want to leave you with is that we're still early. Like, we're still early in terms of the internet, which is 40 years old. We're early in terms of computation, which is, let's say, 100 years old. But even relative to the 500 years since the Enlightenment, that's nothing compared to infinity. So we're the product of this open-ended search called evolution. And our work is an open-ended search for better ways of working. There are going to be some of us in this audience who are working on search problems, in which case they are searching for better search algorithms, which is a bit meta even for me. But what I want to say is, despite the hype, if you, and the feeling that AI might be epicycles all the way down, don't ignore it. Learn about it. Explore the benefits that it can offer, but be alert to those weaknesses, of which there are many. Because with your attention and creativity to those gaps, you might create a new stepping stone. And if you do, then replicate it. Come back and tell us about it. Because then we can follow and see where it leads. Thank you.